Okay, discrete mathematics, we are going to begin section 2.3, which introduces the idea of a function. Now, you've studied functions before, so I want to remind you of a few things. First thing I want to remind you about is that a function is basically like a machine, a thing, an idea, a rule that like takes inputs and then produces outputs. So let me draw a couple of pictures. You're probably used to thinking of a function primarily in algebra class, where you have like an x and a y axis, and you can kind of visualize the inputs and outputs as being, numbers from these continuums. So you have an input along the x-axis and outputs along the y-axis. And then, you have a graph or something like that. So the thing I want to remind you about is the vertical line test. The vertical line test says that this is only the graph of a function. It's only a well-defined function if each input corresponds to one and only one output. So if you draw vertical lines and your vertical line never crosses through the graph in more than one spot, then it's fine, and it's a function. So this one is a function. However, if I tried to graph something with, in, out, and I drew it like this, well, then we have a problem, right? Because a vertical line in this case crosses through the axis of the graph twice. Now the issue with that is that we have an input on our in axis here that corresponds to two outputs. That's called not well defined. Okay, so this would not be a function. So well defined is this idea that we have one and only one output. Okay, so that's my reminder to you. So that idea of the vertical line test captures the basic idea behind a function. What we're going to do now is we're going to sort of generalize that to like the most general idea of a function that you can have. And this relates very strongly to set theory and like connections, sort of maps between sets. And in computer science, you deal with functions all the time as like things that you pass a variable into, and then it might return a value that you might then be able to assign to another variable. So functions are like one of the fundamental ideas that computer scientists work with, as well as mathematicians. So let's first look at the sort of formal definition. So it goes like this: let A and B be non-empty sets. It could be two different sets. It could be the same set taken twice. Anyway, you have A and B, which are non-empty sets. A function f from A to B is a rule that assigns exactly one element of B to each element of A. So the elements of A are your inputs and the elements of B are your outputs, and it's assigning outputs to the inputs, and it can assign exactly one output to each input. And that exactly one, that's basically your vertical line test right there. That's the essential idea of a function being what's called well-defined. Okay? If it gives you an input, if I give a function an input, it's going to give me an output. It's not going to give me more than one, so there's no ambiguity or confusion about what the output is meant to be. Now, the notation that we use for functions is like this. You'll write f as the name of the function, and then you'll write a colon, and you write the input set, arrow, output set. So this arrow is not implies, we're not talking about propositions of truth values. This arrow is being used, we're just using the same arrow, but for a different meaning here. This is just inputs and then outputs. I'm just going to write a couple of statements that kind of capture this idea of well-defined a little better. So one is, we could say, for all A in the set A, okay, so for all elements A in capital A, there will exist an element B in capital B. And then we'll write such that f of A equals B. And I could say there exists unique. I could have put in a unique symbol there, so that there exists a unique B in capital B, such that f of A equals B. And so this notation, that introduces this notation, which I think will be quite familiar from your other math classes. F of A equals B. This is a way of saying if you give the function the input A, the output is B. Another thing I can write is for all A, B1, and B2. If f of A equals B1 and f of A also equals B2, then b1 has to equal b2. So this is a bit of a silly thing. It's basically saying, hey, if f of a is equal to one number and f of a is equal to another number, well, then the numbers must have been the same number. And I said numbers, but actually that's silly because it doesn't have to be numbers. It could be any kind of element. So if f of a equals one element, f of a equals another element, they must have been the same element. That's what it means to be well-defined. So anyway, those are two things you can say that kind of further describe that idea and introduce some of the notation. I just want to wrap up this video with sort of an alternate formulation of this idea of a function in terms of sets. So alternate notion. You can think of a function itself as a subset of the Cartesian product of a and b, like that, where essentially the idea of f of a equals b is synonymous with saying that the ordered pair a comma b is an element of that subset. So this is basically the reason why a section about functions exists in a chapter about sets. It's because technically you can think of a function as a set. It is some subset of the Cartesian product of its a and b, which we're going to introduce vocabulary for a and b in the next video. But yeah, so a nice way to think about this is, when you have a graph of a function from algebra class, right? Like, here's a nice cubic polynomial or something. The entire space that it lives within is R cross R. This is R2. This entire space is R2. And this curve that is the graph of the function f is literally a subset of R2. It is a subset of the set of all possible points, okay? Because that's the space it lives in. So that's functions. Now we're going to learn some vocabulary and do some examples.